This video I will not teach you the complete RCC, just I will touch what are the important bits that can come in RCC. In the previous video I have given you what are the topics that you have to study, but I did not mention the answers. So here I am giving you what are the important questions that can come and what are the answers. I am not going to give any explanations to that, only what are the important questions and what are the answers in this. Okay. And in my previous video I did not mention the important topics in highway because most of the posts are in R and B, and transportation is a very easy topic, so better to study all the topics in highway engineering. I have mentioned that in description of that video, but still as some of the people has sent me a query, again I am telling you that. So below that I have mentioned that you have to read all the topics from highway engineering. Okay, now we will see important topics. As one of the student requested me to do a video on RCC, I thought to do a video on overview at least. Okay, so in this video I will be discussing most important questions that will come from RCC. Okay, I don't give the explanation how it came, but I will tell you what will be the question and answers here. Okay, so first these are the chapters that we have in RCC. First chapter, introduction. Okay, introduction. First important bit is what is alpha, that is coefficient of thermal expansion. What is its importance is RCC means reinforced cement concrete. Okay, in that reinforcement we use steel as reinforcement. Why means both steel and concrete has same thermal expansion coefficient. Okay, that is very important bit. Okay, why they should be same? The question may come, why they should be same means the answer is strain compatibility. To obtain strain compatibility. Okay, remember that is the answer. Okay, next important topic, characteristic strength of concrete. Okay, so this is the graph that shows you characteristic strength of concrete. What is characteristic strength means? The strength at which you have 5% probability of failure for a cube. This is not for concrete, remember, this is for cube strength only. Okay, so you have 5% probability of failure for cube strength based on normal distribution curve. The formula will be FCK is equal to mean strength minus 1.645 into standard deviation. Very important formula. To conduct this test, you will require minimum 3 cubes, and the strength variation between the cubes is limited to 15%. Okay, whatever I have written, everything is very important. Okay, so failure probability of cube is 5%, formula of FCK, 3 cubes, maximum variation, and the failure probability of the structure is 10%. Okay, previously I told failure probability of cube, not concrete. Failure probability of structure will be 10%. How I have obtained I cannot explain it now. Okay, just remember the answers. Okay, so that is about FCK, what you have to remember. Next important, factor of safety. Factor of safety of concrete as per IS 456-2000 is 1.5, and for steel is 1.15. I think you know what is our IS code which we use, IS 456-2000. Okay, so as per IS 456-2000, concrete will have 1.5 and steel will have 1.15. If they are asking in working stress, mostly they will not ask in working stress. If they ask in working stress, for concrete it is 3 and for steel it is 1.8. Okay, mostly it's not so important, but remember these two values, they are very important. Okay, so that is about factor of safeties. Next important topic, load combinations. For a structure, throughout its life period, it will be subjected to different combinations of loads. Okay, every time it will have dead load and live load. We know currently the structure will have dead load and also live load moving in the structure. And wind load, the design wind load may not be there throughout the lifetime, and design earthquake load also will not be there throughout the lifetime. Okay, so throughout its lifetime it will be subjected to different combinations of load. Our structure should be stable to withstand the combinations of the load. So for that reason we will multiply the design load with some partial safety factor. This is factor of safety, this is partial safety factors. Okay, what are that we have to see. Our limit state is designed into two parts, limit state of collapse and limit state of serviceability. The above values what I have mentioned are for limit state of collapse, and the below values are limit state of serviceability. Collapse, serviceability, collapse, serviceability. Okay, so if the structure is subjected to only dead load and live load, multiply the dead load with 1.5 and live load with 1.5. and whatever the value comes, that is your design load for this. Okay. Next, for serviceability, you need not multiply this, you can directly take 1. Why we take lesser value for serviceability means, serviceability factor will be there throughout the life of the structure, but the limit state of collapse, that is for designing, it will come once in a lifetime. Once it comes, the structure will collapse. So we have to design for higher loads in collapse, and for serviceability you have to multiply whatever the load that comes, that is only design load, because that will be acting throughout the lifetime structures. Okay. So serviceability factors like deflection, cracking, shrinkage, creep, okay, all these factors will be there throughout the lifetime of the structure. So we don't multiply any factors, we directly take that load. Okay. Suppose the structure is subjected to dead load plus wind load or earthquake load. Here we have to remember one point. Design wind load and design earthquake load will not come at same time. Okay, this is not a rule that it will not come. Based on the probability statistics that we have seen over the period of years for different structures, we observe that both maximum wind and maximum earthquake will not come at same time. During earthquake, that doesn't mean that during earthquake there will be no wind. There will be wind, but we will not have design wind. Okay. So both maximum wind load and maximum earthquake load will not come at same time. Both wind load and earthquake will cause a severe effect. For a structure, if the wind load acts, it may overturn like this or vibrate, and because of earthquake also, it will overturn or vibrate. So among this, if you take maximum, the design reinforcement for wind load and earthquake load is also quietly similar. Okay. So in limit state of collapse, it is 1.5 or 0.9 for dead load. What is this 0.9 means? Here you can see dead load plus wind load or earthquake load. There is no live load here. When there is no live load in the structure gravity effect is very less because there is no live load. So when a wind load or earthquake load hits, there may be possibility of overturn without collapse. So if there is a possibility of overturn, the effect of dead load will reduce because it has overturned. There will be no much weight in this direction. So the dead load should be multiplied only with 0.9 when it is overturning, and 1.5 if it is not overturning. If they mention as overturn, multiply 0.9. If not mentioned, 1.5. Okay. Okay. Next, coming to wind load and earthquake load, this one is for serviceability, 1.5. So wind load and earthquake load should be multiplied with 1.5. Only dead load should be multiplied with 0.9 if there is overturning. Otherwise, it is 1.5. Next, coming to limit state of serviceability, same you have to multiply 1 and 1. If the structure is subjected to dead load plus wind load plus live load or earthquake, dead load plus live load plus wind load or earthquake load, then you have to multiply 1.2, 1.2, 1.2, 1.8, 0.8 for serviceability. Okay. So all the above values are for limit state of collapse, all the below values are for limit state of serviceability. Remember this table. How we design means, we see what is the maximum load that is coming in different cases, and we design for the maximum load. That will be our design load. Okay. So more than this we cannot consume time for this. Okay, next, coming to stress strain diagrams of concrete and steel. In stress strain diagram of steel, the important factor that we have to remember is Young's modulus of steel does not depend on grade. It is always 2 into 10 power 5 Newton per mm square. Okay. And Young's modulus of concrete is 5000 root of FCK. It depends on the grade of the steel. Okay, sorry, grade of the concrete. Okay, that we have to remember. Next, if you observe the stress strain diagram of concrete, the concrete will yield at 0.002 strain, important value. This is called yield. After yield, there will be no rise of stress, only strain will be there. This is failure point. Okay. So when the concrete is subjected to bending, you will have yield point at 0. This is for bending case, not compression. So yield at 0.002 strain and failure at 0.0035 strain, and design strength is 0.45 FCK. Okay. Remember, cube strength is FCK, compressive strength is 0.67 FCK. Okay. It is based on some cylindrical strength, the concept of cylindrical strength. Just remember, cube strength is FCK, compression strength is 0.67 FCK, design strength is 0.45 FCK. For compression strength, if you divide with 1.5, then we will get 0.45 FCK. Okay, that is the important things we have to remember. Apart from that, there is one more important bit that we have to remember. Tensile strength or flexural strength of concrete is 0.7 root FCK. And sometimes it is also represented as modulus of rupture. Even if they say modulus of rupture of concrete, The answer is 0.7 root FCK. Okay, these are the important bits that you have to remember from introduction chapter. Next, coming to single reinforced beam. Single reinforced beam also one of the important topic. Mostly you will get questions from introduction. Highest number of questions will come from introduction only, most probably in government exams. So coming to singly reinforced, first important thing what we have to see is cross section of the beam. If you see the cross section of the beam, okay, these are longitudinal steel bars and this is a shear stirrup and this is the beam. Okay, in this what we have to know, from the end of compression fiber to the center of the steel, it is called effective depth. Next, from the center of tension steel till the end of tension fiber, it is called effective cover. From the end of tension steel to the end of tension fiber, it is called clear cover. That is the difference between clear cover is measured till the end, effective cover is measured till the center of the steel. So effective cover will be clear cover plus half of the dia, what we have used for longitudinal reinforcement. Okay, that is one important bit we have to remember. Okay, next topic, stress block. What is stress block means? Previously we have seen the stress strain diagram of concrete. Yield is at 0.002 and failure is at 0.0035. That is called block. You can see the stress strain diagram of concrete is similar to block. In this block you have to remember some numbers that are called stress block parameters. What are that? Let us see. The entire if you find the area of this and multiply with breadth, we will get what is the compression force. That compression force is 0.36 FCK BXU. That we have to remember. That will be acting at a depth of 0.42 XU. What is this XU means? Depth of neutral axis measured from top of compression fiber. Top compression fiber to neutral axis is called depth of neutral axis, represented by XU. Our compression force will be acting at 0.42 XU. Our design strength is 0.45 FCK, which I have already discussed. And the yield point will be at 0.43 XU from the top of compression fiber. So this 0.43, 0.45 and 0.42, this will govern the shape of the stress block. So these are called stress block parameters. Okay, 0.43, 0.45, 0.42, compression force 0.36 FCK BXU, tension force 0.87 FY AST. To find this neutral axis, we have to take total compression force is equal to total tensile force. Then you will get what is the neutral axis. Okay. Once you get what is the neutral axis, you can find the resisting moment of resistance mu using the formula 0.87 FY AST into D minus 0.42 XU or 0.36 FCK BXU into D minus 0.42 XU. This is nothing but, as this is a couple, force multiplied with lever arm will give you what is the moment. Okay, so either you can multiply compression force or tension force. In a couple, both the forces should be equal in a couple, we know. So you can multiply either compression force into lever arm or tension force into lever arm. Okay, if they are giving you the area of steel, means you have to check whether it is under reinforced or over reinforced. Okay, if they are not giving you the area of steel and you cannot find it, so directly find from 0.36 FCK BXU. Okay, if there is a scope for checking whether it is under reinforced or over reinforced, check that and apply the appropriate formula. If there is no scope, any formula will give you the answer. Okay, how to check whether it is under reinforced or over reinforced means, after calculating XU value, you have to compare with this based on the grade of the steel you use. Okay, so this is the value of XU max by D. So calculate XU max by D from this table. So for 250 grade it is 0.53, 415 0.48 and 500 0.46. So from this chart we will get XU max value. Okay, this XU max is for balanced section. Okay, if the calculated XU value is less than XU max, it is under reinforced. You have to go with first formula. If calculated XU value is equal to XU max, then you can use any one of these formula. Instead of using any one of this formula, we have a shortcut if it is a balanced section based on grade of steel. Fu250 0.148 FCK BD square, direct answer. 415 0.138 FCK BD square, direct answer. 500 0.133 FCK BD square, direct answer. Okay, so directly you can find the mu limit if you have a balanced section. If XU value calculated is greater than XU max, then you have to go with 0.36 FCK BXU into D minus 0.42 XU. Okay, so that is about mu. So we have finished the stress block. XU max, MU limit, MU. Next, AST minimum. Next important bit, what is the minimum area of steel we have to use in beams. AST minimum by BD is equal to 0.87 by Fy. Okay. This formula is important. If they ask the reason why we are using AST minimum, the reason is to provide the enough ductility to the beam. That is the answer. Okay. Next, AST max. AST max is 0.04 into B into D. This is not small d, this is capital D, which is total depth. Okay. And if they ask what is the percentage of steel can be calculated by the formula AST by BD. This is small d, this is capital D. See the difference into 100. Okay. So these are some important bits that can come in single reinforced beam. Next, coming to double reinforced beams. When do we use double reinforced beams? A single reinforced type of section we have discussed, under reinforced, balanced and over reinforced. It is not advised to design as over reinforced beams because over reinforced failures are sudden and under reinforced failures will take some time to heal. And another important bit in single reinforced beam, after the failure of the structure in over reinforced beams, the neutral axis will move down after the failure. In under reinforced, it will move up after the failure. Okay, so that is one important bit that you can remember. Okay, so when we use doubly reinforced means if the beam is over reinforced and single reinforced, we will have two options to redesign. One is to increase the depth, second one is to go with double reinforced. Okay, so if it is over reinforced and the depth is restricted, then the only option is you have to go for doubly reinforced. Okay, that is the situation where we go for double reinforced when the depth is restricted. Okay, but comparatively, doubly reinforced are less economical compared to single reinforced because the strength of the steel in compression we cannot utilize completely. So compared to double reinforced, single reinforced are economical. Okay, and the second thing, what is the stress subjected to stress subjected to compression steel in doubly reinforced, that also we have to remember. How to find the FSC value based on the d dash by d. What is d dash means? Depth of compression cover. Whatever the stress that is coming in the steel is FSC, that is steel under compression, FSC. So for FE 415 grade and FE 500 grade, based on d dash by d value, you have to remember the FSC values. If it is FE 250 grade, directly you can take FSC as 0.87 Fy. Okay, that is one important bit. Next important bit is where will be this d dash value in XU depth. Okay, so for a depth of XU the change will be 0.0035 and for a depth of XU minus d dash the change will be ESC. Okay, so here I did not mention the strain values. Okay, but this is how you can calculate what is the strain in compression steel. This is stress in compression steel, this is strain in compression steel. Okay, they can ask anything more than this in doubly reinforced. You may not get any other questions like finding the moment of resistance. It will take some time, so that's not important, we can leave that. Next topic, flanged beams. In flanged beams, first important topic is effective width of the flange. In flanged beams we have two types, that is T beam and L beam. Okay, so if it is a T beam continuous, the effective width of the flange is given by L0 by 6 plus 6 df plus breadth of web. If it is isolated beam, if it is not continuous and isolated, the formula is BW plus L0 by B plus 4. Okay, here they may ask you another cross check also. So it should not be less than or equal to C, and this should not be greater than B, and this also should not be greater than C. Sorry, C by 2 because this is L beam, and this should not be less than B. Okay, anyway, it is L beam. Okay, so that is about effective width of the flange. Next, coming to moment of resistance in T beam. For balanced section, we check df by d less than or equal to 0.2. For unbalanced section, we see df by xu less than or equal to 0.43 case. So if any one of these case satisfies, then you have to use this formula for moment of resistance of T beam. And this formula, if df by d greater than 0.2 and df by xu greater than 0.43, then you have to use this formula. In the place of df, we get something called yf given by this formula. Okay, so the formulas you can find in the IS code also. Okay, it's not so important. And suppose if the neutral axis is within the flange, then we don't consider it as a flange beam, we consider it as a rectangular beam only. After finding the approximate XU value, if the neutral axis is falling within the flange, then you need not apply any of this, directly you can proceed with the rectangular beam design. If it is falling in the web, then you have to check case 1 or case 2 and apply the appropriate formula. Okay, so that are the important things in T-beam. Next, coming to shear chapter. In shear chapter, first important definition is tau V given by VU by BD if it is a rectangular section. If it is a tapered section, then the formula will be VU plus or minus MU by D into tan beta divided by BD. Okay, so if it is a tapered section like this, okay, this angle is beta. So if it is a tapered section, this is how we have to find the shear stress at any depth. Okay, so to use plus or minus, here as this is a cantilever, we can see the bending moment is increasing in this direction and depth also increasing in this direction. If both bending moment and depth increases in same direction, then you have to take negative sign. Suppose if it happens like this, so here you can see bending moment is in this direction, depth is increasing in this direction. In this case, you have to take the positive sign. Okay, that is about nominal shear stress tau V. Next important factor tau C, that is shear strength of concrete. Okay, so if tau V is less than tau C, less than or equal to tau C, then we have to use minimum shear reinforcement. Okay, minimum shear reinforcement formula is given by ASV by B into SV. This SV is suffix. A suffix SV is B into SV. This SV spacing is equal to 0.4 divided by 0.87 Fy. Okay, so this ASV is ASV minimum. Okay, suppose if tau V is greater than tau C, then we have to find something called VUS, which is given by tau V minus tau C into BD, and the spacing is given by 0.87 Fy ASV D divided by VUS. Okay, and also if you have inclined stirrups, you will have different formula, where this ASV is area of stirrup, only one cross sectional area of one stirrup. If you are using a two-legged stirrup, then you will have cross section 2 into pi by 4 d square. Okay, that is ASV. So from that we have to calculate what is the spacing. After calculating the spacings, the spacing that you have to provide is minimum of the SV that you have calculated, 0.75 times of effective depth and 300 mm. Among this, we have to take the minimum value as spacing. Okay, so that are important things about shear design. And so we have covered the ASV minimum, SV, tau C. Okay, tau C max. In shear, there are two types of failures that can occur. One is because of tau V. If you increase the tau V, then near the support we get something called diagonal cracking. To avoid the diagonal cracking, we provide bent up bars. Suppose if the tau V value equals to tau C max, then it fails in something called diagonal compression, not diagonal tension. Previously it was diagonal tension. If tau V is very high, then it reaches a value called tau C max because of diagonal compression failure. Then we have to redesign for the shear. Okay, so that are important topics about shear. Next, coming to bond. So these are the topics in shear. Next, coming to bond. So bond is decided based on a development length formula, phi into sigma is divided by 4 tau BD. Okay, this tau BD values you can take from the table. If you have a HYSD bars, HYSD means FE 415 grade and 500 grade, we have to increase the values by multiplying with 1.6 times. Similarly, if the bar is in compression, we have to further increase it by increasing 25% tau BD. So from the table, whatever the value you get, suppose if the bar is HYSD and it is in compression, example is column. In column the bars are in compression And if you use HOSD bars, the whatever the values you have in tau BD, you have to multiply it 1.25 into 6. This will be 2 times. So 2 times of tau BD you have to make. That is one important note. And this development length is equal to anchorage plus bent. Okay. So anchorage means the extended length and plus bent. Okay. So suppose you have a reinforcement bar here till the support. Okay. So from the support we will extend this bar. This extended length is called anchorage and this is called bent length. Okay. This LD should be equal to anchorage plus bent length. Okay. So as I said, anchorage is just the extended length. How to calculate the bent length means for every 45 degrees we will have 4 times of diameter as the bend length. So if you provide 90 degrees bend, then we will have 8.5. So which means that from the support, if I extend some 25 diameter length and I provide a 90 degree bend, it means that I have provided a development length of 25. I have provided a development length of 25 plus because of 90 degrees I get 8.5. So I have provided 28.5. Checking the development length, we have a formula. We should arrange maximum like this, that is the development length is moment of resistance by shear plus anchorage. Okay, so this is how we can arrange if it is a simply supported. For fixed support it is 1.3 m divided by v plus L naught. Okay, so we can decide what is the anchorage we require and what is the bend length we require. So based on that, by calculating this formula we will get how much development length we require. After getting the development length, how much anchorage we have to provide, how much bent length we have to provide, based on this we will decide. Okay, these are important things in bent up. Okay, so if you have a 180 degrees bend, so for each 45 you have 4.5. So for 180, 4 into 4 means 16.5 bent up length. Okay, so the development length is a combination of anchorage and bent up length. Okay, so that are important things in bond. Coming to torsion chapter. In torsion chapter, the important topics are equivalent torsional stress and equivalent torsional stress because of shear and equivalent torsion because of bending. That are the two very important. Okay, so what is that? The total shear is equal to the shear that is coming because of bending and the shear that is coming because of torsion. So the torsion can be converted to shear like this. This is called equivalent shear stress. Similarly, we have equivalent bending moment. So given by whatever the moment you get in bending plus because of torsion we get T into 1 plus D by B. This is total depth, remember, divided by 1.7. Okay, so this is the moment due to torsion. This is the shear due to torsion. Equivalent shear stress and equivalent bending moment. So suppose if this is okay, so this value is assumed as MT. Suppose if MT is greater than MU, then we have to design a doubly reinforced by assuming MU2 as MT minus MU. Okay, so that is one checklist. So we have to provide additional compression reinforcement also if MT is greater than MU. Okay, so that is moment due to torsion and shear due to torsion. These are important in torsion chapter. Coming to compression members. In compression members we have 3 types of columns, that is axial column, biaxial or uniaxial and biaxial column for a short columns. Okay, so I hope you know what is short and long columns. LE by D greater than or less than 12. So for long column it will be greater. Okay, so for long columns you just remember the formula of reduction factor. Apart from this, long columns are not important. Coming to short columns, if it is axial load, then the strength is calculated by PU is equal to 0.4 FCK into area of concrete plus 0.67 FY into area of steel under compression. And you have something called perfectly axial, which is given by 0.45 FCK into area of concrete plus 0.75 FY into area of steel under compression. This is perfectly axial, this is axial. So whether to decide it is axial or not, or axial or uniaxial, then you have to calculate something called eccentricity, E minimum, which is given by L by 500 plus D by 30. If this is less than or equal to 0.05 D, then we consider the column as axial column and we calculate according to this. Okay. And another checklist here is, if we use helical ties, then the strength value should be increased by 5%. Means this formula should be multiplied by 1.05 if you are providing a helical ties. Okay, for normal ties you can calculate the formula like this. Okay, so and some more important things that you have to remember is failure strain. Failure strain in axial case is 0.002 and minimum area of steel that you can provide is 0.8% and maximum area of steel that you can provide is 6% and minimum number of bars that you can provide is 4 for rectangular or square and 6 for circle, okay, and 8 for octagon. Okay, so this is also one of the most important bit. And minimum dia that you can use for column is 12 mm. Okay, so that are some important specifications that you can remember for axial. Okay, uniaxial design requires something called interaction curves. Okay, so as they cannot provide interaction curve in the exam. In uniaxial, what you have to remember is the maximum failure strain is 0.0035 minus 0.75 times of strain at least compression fibers. This is very, very important. And biaxial, it is highly impossible to get a question from biaxial. Okay, but biaxial has one interaction equation. Just see that equation, or else you can leave that biaxial equation. And for long columns, we have reduction factor. Just see that reduction factor and leave that long columns. Okay, so that are some important things that I can say here. So apart from this, minimum diameter of lateral tie is pi by 4, that is whatever the dia we are using for maximum dia we are using for longitudinal reinforcement, and 6 mm. So among this we have to take maximum for diameter of lateral tie. Okay, that is also one important bit that we have to remember. And spacing of lateral tie is also one of the important. Just see what is the spacing for lateral tie. Coming to slabs, for state Govt jobs, you will have very less questions from slabs, but still the possibility questions are, the maximum dia that you can use is capital D divided by 8, and aspect ratio Ly by Lx, if it is less than or equal to 2, we take 2 way. This equal to can be placed anywhere, no problem, it depends on our design. And if it is greater than 2, we take it as 1 way. Okay. And coming to distribution steel, if you have 1 way slab, then you will have distribution steel. If it is 2 way, in both the direction you will have main steel only. Suppose if you have a distribution steel, then the minimum area of steel that is provided is 0.15% for Fe250 steel and 0.12% for Fe415 and 500 grade steel. Okay, and if it is a distribution steel, the spacing required is 450 mm, maximum spacing 450 mm for distribution steel and 300 mm for main steel. This is for main steel and this is for distribution steel. Okay, and these are minimum area of steel values that we have to remember. Okay, so that is about minimum area of steel and spacing and dia. Okay, so maximum dia, 1 way, 2 way, minimum area of steel, spacings. Okay, these are some important bits that we can see from slabs. Coming to footings, first important bit in footings is to find the depth. So the approximate depth can be found by the formula tan beta equal to 0.9 into square root of 100 q naught by fck plus 1. Okay. So using this we can approximately find the depth. So you can find the tan beta here, opposite by adjacent. So if you substitute in this formula, so here q naught is bearing capacity of the soil, fck is grade of the concrete. So this is concrete whatever you have, and here you will have soil. Okay, so the soil will have bearing capacity and concrete will have fck. Okay, so depending on the grade of the concrete we are using for the foundation and the bearing capacity of the soil, you can decide the approximate depth. Okay, this is one important formula. And critical sections. Critical sections for bending. If this is your column and this is your footing, critical section for bending will be at the face. Remember, this is at the face for bending. And for one-way shear, it will be at a distance d. And for two-way shear, it will be at a distance d by 2. Okay, so this is the critical section. You can see this is two-way shear or punching shear. Okay, this is one way and two way. The depth of the foundation is calculated using three criteria: bending, one way and two way. If they ask you a question like first we have to start with which criteria, then the answer is one way shear. In most of the textbooks you will be seeing they will start with bending, but actually you have to start with one way shear to calculate the depth of the foundation. Okay, that is also one important bit you have to remember. Next, coming to serviceability, first thing is cover. How much cover we have to provide? So minimum cover for slabs is 20 mm, and for beams you have to provide 25 mm, and for columns 40 mm, and for footings 50 mm. Okay, so that are minimum covers you have to provide. And deflection, to carry for deflection limits we have to remember something called A value. Even these A values are important for slab also, for cantilever, for simply supported and for continuous. Okay, so that is 7, 20 and 26. Okay, A value is nothing but the ratio of length divided by depth. Okay, so the length divided by depth value should be 7, 20 and 26. Okay, so by assuming this, whatever the deflection that comes immediately after construction, the maximum deflection should be less than or equal to, the maximum deflection should be less than or equal to L by 350. And throughout this is immediately after construction, means if you remove the shutterings, the maximum deflection that should come is L by 350. So if you remove the shuttering quickly, then the deflection will be more than L by 350. So we don't remove the shuttering immediately, we place at least for 10 days per slab. Okay, and throughout the life the delta should be less than or equal to L by 250. Okay, so that are some important bits. Lateral stability. For lateral stability, if it is a cantilever, the length should be limited to 25b and 100b square by d. Okay, for SSB and continuous both you have same rule, 60b and 250b square by d. Okay, so these are some important bits from serviceability. Okay, cover, A values, deflection limits, this is immediately after removing the shuttering, this is throughout the life of the structure, and cantilever, and this is for lateral stability for cantilever, lateral stability for SSB and continuous. Okay, in serviceability, in deflection another important criteria are shrinkage. Okay, in shrinkage what you have to remember is the maximum shrinkage strain is 0.0003. Okay, that is also one important bit from shrinkage. Okay, so that is about serviceability. Okay, so next coming to pre-stressed concrete. In pre-stressed concrete we have to remember some specifications, like in pre-stressed concrete we have pre-tension and post-tension. Okay, in pre-tension we have Hoyer's method, and remaining Yodel method or whatever method comes, all will come in post-tension method. In pre-tension we have Hoyer's method, okay, remember that. And in pre-tension minimum grade that you can use is M40, for post-tension you can use M30, okay, that's all. And maximum deflection, maximum upward deflection in pre-stress, as we place the pre-tension wires at the bottom, we get hogging when there is no load. So maximum upward deflection is limited to L divided by 300, okay, remember that is also an important bit, okay. Next for if you get any problematic questions, then in analysis read all the type of questions for finding stress at the bottom fiber and stress at top fiber, and losses. In losses also try to read all the types of losses if possible. So in losses we have elastic deformation loss, shrinkage loss, friction loss. Some are long term and some are short term losses, okay. See which are long term losses and which are short term losses and read accordingly, okay. So from whatever the theory that comes in pre-stress, read the theory part. Analysis, most probably I don't think you get analysis questions from analysis because calculator is not allowed. But in losses you have some theory like which are long term stress and which are short term stresses, and some small formulas. Suppose if you take the loss of elastic deformation, the formula is simply M into FC, which is very simple formula. So there is a possibility of asking question from that, okay. So like this in losses, if you see simple formulas, read that formulas and review the remaining pre-stressed topic, okay. So that's all about important bits in RCC.